While electronic voting machines have significantly modernized modern elections, ensuring definitive voter authenticity remains a high-stakes challenge prone to manual errors or identity impersonation. To solve this problem, we engineered the secure, dual-core, Biometric Electronic Voting Machine. Built around the powerful AtrivaTECH PicUNO platform, it integrates fingerprint authorization natively to guarantee a secure, immutable, one voter, one vote election environment. The project is powered by the AtrivaTECH PicUNO, featuring the dual-core RP2040 microcontroller. Under the hood, this architecture replaces traditional looping code with a 100% event-driven, multitasking setup powered by FreeRTOS. The system exploits the dual-core RP2040 chip. Core 0 is fully dedicated to managing the R307 fingerprint sensor in a zero CPU sleep state, while Core 1 effortlessly drives the main state machine, software timers, and background buzzer tasks. Key system capabilities include biometric identification via fingerprint matching, strict duplicate voting prevention, 100% offline edge execution for maximum defense against external cyber threats, hardware-backed real-time clock timestamping, tamper-evident audit trails saved onto FAT32 storage. The hardware matrix consists of the AtrivaTECH PicUNO board, an R307 biometric module, an Adafruit data logger shield, multicolored NeoPixel indicators, and hardware-to-bounced voting matrix buttons. To safeguard the 3.3-volt RP2040 logic lines from standard 5-volt UNO shield voltages, the shield's standard I²C pins were safely isolated and rerouted directly to level-shifted digital pins 4 and 5. System boot and peripheral check. Watch what happens as we power up the machine. The internal FreeRTOS system instantly boots up and performs an automated self-test on all vital connected subsystems. The real-time clock synchronizes. The fingerprint sensor establishes communication. The SD card is validated, and the system logs system boot to the internal logs before shifting to its standby polling state. To open up polling, the booth officer must first authenticate using the system's pre-registered master fingerprint. With the system active, the first voter places their finger on the sensor. The machine searches its local data array, confirms registration, and prints the user's information along with their specific ward number to the LCD display. The voter enters a 30-second window, presses their chosen party button, and the system blinks the party LED and issues a clean buzzer tone to acknowledge a successful vote. What happens if an unregistered citizen attempts to breach the system? Here, a rogue fingerprint is placed on the R307 lens. Core 0 flags the authentication anomaly immediately. Core 1 updates the UI to show access denied, lights up the global NeoPixel red, and fires off a continuous alert tone via the independent audio task to warn the nearby polling staff. Next, a regular registered voter approaches the machine. Core 0 instantly finds a valid signature match inside the voter database. The system welcomes the voter, unlocking the hardware interrupt lines for the voting matrix. After confirming their credentials against the storage registers, the voter completes their selection. The system confirms the vote, writes the update to the file system, and clears the user interface for the next transaction. Then the machine goes back into standby, waits for another registered citizen, verifies their identity via the scanner. Once more, an unauthorized finger is scanned. The event-driven framework isolates the event, blocks the voting matrix, locks down the system with a vibrant red visual indicator, and alerts election officials that an invalid voter has been blocked. Preventing duplicate voting attacks. Here we test our primary security feature. A voter who has already participated earlier attempts to scan their finger a second time. Although the fingerprint itself is valid, the main logic engine catches that the user's voted status boolean is set to true. The LCD prints already voted, the buzzer goes off, and duplicate voting is fully stopped. Once all voting windows are closed, the administrator accesses the concealed hardware result switch. Holding down this physical switch safely breaks the polling loop and transitions the operating state machine directly into result mode, locking down the biometric task completely. Inside result mode, the party selection buttons switch behaviors. Instead of casting votes, they function as query selectors. Pressing individual buttons pulls the encrypted result tallies out of memory and shows the data directly on the LCD screen, allowing officials to securely view counts without any risk of altering the raw election logs. Let's extract the MicroSD card from the data logger shield and inspect the generation logs on a desktop PC. The machine saves all activities across 3 separate, clear CSV and text files. Opening Audit, log shows the power of our real-time logging engine. Every event, ranging from initial power-on sequences, fingerprint matching operations, successful votes, and failed access attempts, is timestamped with millisecond precision from the RDC chip. Next, results. CSV displays our clean party totals, while voters, CSV reveals the complete voter register, proving that the user's data was modified to flag them as having voted. This creates an unalterable, transparent, and completely verifiable ledger of the election. Voters, CSV. This file functions as our local, secure voter registry database right on the edge. It stores all the authorized voter profiles beforehand, mapping unique fingerprint ID number, their full name, date of birth, and assigned ward number. Because the system runs completely offline, this internal cross-referencing structure ensures that voter identification happens instantly and securely at the local device level without needing a network connection.